Thank you for having me. My name is Professor Cheng. Today I'm going to present a topic on YOLOv5 and Residual network for intelligent text recognitions on degraded serial number plates. As for introductions, in the ship engine rooms, the serial plates face deteriorations due to maintenance, as you can see from the right-hand side, wear, tears, and oil stain, making the alphanumeric character hard to read. So identifying the correct serial number is crucial for obtaining the fitting spare parts. If there's some parts that need to change in the engine, for example, that's very important because we do not want to install the wrong components that can damage the machines and endanger the crew member on board the ships. The Sync text recognitions (STR) methods were computationally heavy, especially in the deep learning, had increased interest on that. Bayesian optimizations to detect regions of interest, in short ROI, and classify serial numbers on Bannock serial number recognitions was performed, and there's a brief literature on that. Convolutional neural network CNN is effective, but challenges arise from diverse text patterns and backgrounds. Residual networks, in short ResNet, and densely connected convolution network DenseNet, combined with the bidirectional long short-term memories networks, in short BiLSTM, can be computationally intensive. So it means you can see that the ResNet will be very good in the literature, and it states that it's good in addressing degradation issues. This diagram on the right hand side just show using the ResNet 152 model without the guidance of the bouncing boxes. Automatic license plate recognitions using only Loop 1's version 5, in short YOLOv5, for license plates detection achieve 98% accuracies. That is what we can see in the literatures, and it's typically used for ROI identifications, and transformation ResNet non-attentions is employed for classifications, achieving a very good accuracy of the 93%. YOLOv5 offers significant advancement in speed, accuracy, simplicity, and flexibility, making it a preferred choice for various real-time applications requiring fast and accurate object detection capabilities. So hence in these papers, we will be using the YOLOv5 model for detection tasks, mainly on the ROI, while using both YOLOv5 and ResNet are considered for the classification task, mainly for identify the alphanumeric. So the methodologies you can see from the right hand side is that we propose basically these steps to attain the optimum classification outcomes. First, we have the input image, so we crop basically getting the region of interest, and we have the second model which create the bounding boxes, and then with that we classify using the YOLOv5 and as well as the ResNet 152. So in these studies, we will refer to the first YOLO model as model 1 and the second as model 2 here. Alright, so model 1 will be YOLOv5 here, and the second model YOLOv5 will be under the name of model 2. So one is for detections and one is for the classifications of alphanumeric characters. So for these papers, we are using the RoboFlow. So it's basically an applications to streamline the intonations and the augmentation process. So the custom data can be easily intonated and augmented to create a larger sample size without collecting more image. So here we just give a snapshot of the processes from the first step to assign the image for intonations to intonation page, creating new data versions here, followed by on the left bottom side you will have this exporting this as a PyTorch, followed by we consolidate all the data set, which I call this as the home page, and then we can download the codes and then use it in the our Jupyter notebooks or even the Spider SDK. So for dataset 1, the first custom dataset mainly consists of the random serial number plate from random type of machineries or parts, as you can see from here on the right hand side. The focus is to annotate the plate portion only, such that the model 1 can identify the serial plate portion, which is distinct sharp edges and the rectangular shape, as you can see, sharp edges and rectangular shapes. So the first dataset consists of around 470 images, and we augmented to comprise more images, like 1,134 images in total. So we can split them for training, validation, and followed by testing. So the final dataset was named as the OCR FYP on here as well. You can see on the right side 996 images, validation 91 image, and testing 47 images. And for the dataset number 2, it mainly consists of marine types of machineries that you usually found on boards. Popular engines such as the MAN, BMW, and Caterpillar were chosen. So it consists of both deteriorated and the good condition serial plates, and also it consists of definitely some text and model names will be annotated. And these annotations techniques will prevent the model from creating unnecessary bounding box that we do not want it to bound, like this what we call the screw or something that we fastened onto this engine. We do not want to have bounding box on this. And these annotations label will be created for 0 to 9, A to Z, as this model will be used to train the ResNet, which is 152, the 152 layers model. And we expand it to include 1005 images. We speak for the validations and testings. And through the annotation process, extra label were inevitably created due to the typographical errors, which were subsequently removed to prevent potential training inaccuracies. And we just save it as a file name called alphanumeric characters. You can see some of the process that we have done on the right hand side. The MEs and the AZ dataset, which is a dataset we used to train the ResNet. As you can see, ResNet is to classify the alphanumeric characters, total 70,000, and A to Z dataset consists of 26 labels, each contain 1,260 grayscale image, total up to 32,760 image. And this both dataset is combined using some of these commands. I believe most of you guys know that, concate dataset modules, and both will be combined, and then we split the combined data sets into 80% for training and 20% for validations data set. So the right hand side just pretty show the kind of code that we have written on that. So for pre-processing, which we always know that we need to pre-process, and especially for our case, our data set is not a lot, so we need to do augmentations. So during the collections of training of Model 2, it was observed that despite some training, model could have achieved better performance on unseen data sets. So we try to enhance the model robustness by doing some augmentations, and this process can be done easily in the RoboFlow kind of platforms. And there's a diverse range of serial plates in all data sets, and it's very hard to apply a one-size-fits-all kind of approach. And therefore, this study will focus on the most common type of serial number plates, characterized by engraved letters with a color similar to the backgrounds. So this basically some of the pre-process methods that we have done for our input image. So basically, we try to also create a custom data set optimized for ResNet 152. Custom meaning that after the augmentations, meaning that we have more data sets. And we also want to build a more robust ResNet 152 models, and the model was fine-tuned, and the custom data set already annotated in the RoboFlow to save times. So this is the process that I mentioned in the previous slides, that we use the commands to combine them, and then later on we try to use the augmentations to increase the number of data sets. So for training wise, basically you follow the flow on the left hand side. So initial neural network, the YOLOv5 object detector classifier, identify and crop the region of interest. And this crop ROI, which is what we have done, will be used into the second YOLOv5 neural network model, which is here. Okay, this is the first YOLOv5 model, and this will be the second. And finally, the image of the bounding boxes undergo the classification using the ResNet 152 model, focusing on characters within the bounding boxes, which we are basically trying to classify the alphanumeric characters. And definitely we know that when we do trainings, there's a lot of hyperparameters. So one of them is the number of epochs and the batch size as well. So we actually use a bit of try and error approach. So we definitely want a bigger batch size, but we have limited resources. So we use a batch size of 16s, and we adjust it as required. And we also have the number of these epochs as 300s, followed by selection of initial weights. Definitely ResNet, we use the what I call their weights, but for the other let's say YOLOv5, we try to select some initial weights, and we try to use a weight that can accelerate the conversions by capitalizing on the previous knowledge that we have. And we also have what I call the transfer learning, can take place through various methods. Data set like what we have, dataset 1 and 2, we try to annotate it in a YOLOv5 PyTorch format. We underwent the augmentation in the RoboFlow, the platforms, and this dataset will export, as you can see, and for YOLOv5 trainings. So here we just use our laptops that is 2.5 GHz and the NVIDIA GeForce RTX 2060 GPUs. So for trainings on the crop image dataset, the training will be conducted on the publicly available dataset that we have, and the model optimal new weights will be saved and further trained using the custom dataset. And this weight basically corresponds to the smallest variance of the YOLOv5, and we initially train it on the diverse array of objects within the COCO dataset, which is the common object in context, which comprises 80 different object classes. So this weight is tailored to extract a fundamental feature, which is the .pt files, such as edges and corners from input image, and also which is quite pertaining to the serial number plates. And however, this COCO dataset did not undergo specific trainings for classifying the region of interest pertaining to the serial plates. So this model will undergo some fine-tunings using the serial plate dataset, necessary updates to all layers accordingly. So the training on the crop image data, which is basically we are more focused on the serial number now. So we fine-tune the YOLOv5, which is basically a single core of lines that we all know that, and that's the code we set the image as a 416 by 416 with a back size of 16 and 300 epoch. And the training lasts for around less than 1 hour, and the precision score is 88.3%. And the recall score is 75.9% based on these 70 images. And for serial plates, the precision reach can be reached to up to 92.8% and recall 82.2%. And this result demonstrates the model efficacy in the serial plate detections. And while increasing the epoch could be potentially good, but we also need to look at the results that's quite adequate, as the weight will adjust to the custom data set during the fine-tunings. So you can see some of the results for trainings and validations. You will see that definitely the training progress could have higher accuracy by increasing the epoches. And however, the validation loss graph shows some sign of the stagnations, okay, and the possibility of increased loss with the increased epoch. So for the test, we basically use a 5 unseen image, and 5 image will all properly crop up with a varying size of serial plate, as you can see on the right hand side for the testing. So one is the first row is the original, and the second row is the crop ROI. And for the training for the bounding box, which is the model 2, actually we have the second YOLOv5 models, which basically to do that. And here we involve calling and training on these YOLOv5.pt weights. And this model will exclusively train on the custom dataset, which is after the augmentations. So we apply the model trained on the serial plates without any pre-processing augmentation for this case. And we mentioned about this image size is 640 by 640, 16 sample batches, 500 epoch for this, and we took about nearly 6 hours. Overall precision score of 77% for 36 label and 53% of precision score, as you can see from here. And we suggest that not more than 500 epoch, because it doesn't really benefit if you do more than that. And the validation loss show a rising trend after around 300 epoch. And the augmentation techniques that we use here is the color inversion, contrast enhancement, and some of these combinations to provide model with more diverse data to train. And you can see from here, the dataset was retrained again using the pre-trained weight of best.pt, which we use to store the weights, and it's complete at around 1.3 hours at around 419 epoch. The accuracy is 81% with a recall score of 69.4%, and the precision score improved around 4%. You can see from our calculations, and which basically you can see there's a sign of noise actually, and this probably contribute to the imbalance in the class samples compared to the training data set. And we also have these trainings on the YOLOv5 S.pt weights, combination of serial and also some fade serial plate provide better results on 500 epoch, taking around 2 hours. And the overall precision was measured at 82%. It improved by 1.2% as compared to the previous steps, and slightly higher in terms of recall score of 72.1% as compared to the 69.4%. Validation loss improved. It basically give a less noisy graph. And when using this model with the crop image from this model 1, the model correctly classified 86% of unseen image on this good condition serial plates. YOLOv5 could classify the alpha numeric character correctly, except making some mistake on, so instead of G, it says C, right? So this is something that we have observed. And this is just a snapshot of some of the photo that we saved it. And Residual network 152 is used to classify what I call the alpha numeric characters, and we train on 1000 classes, and fully connected will be replaced by newly linear layers, and the new layers will be 36 output features. And we have this data loader is set up for batch size of 32 with the shuffling of the training data set, which we set to true. And the model will train in 300 epoch. You can see it took about 22 hours, and basically early stopping was observed in around 131 epoch with training accuracy of 99.98% and the validation accuracy of 95.95% on the means and the AZ datasets. And you can look at the classification of the alphanumeric characters. Since it was trained in the means and the AZ dataset, it wasn't produced quite a good results. The ResNet 152 model was retrained on the custom dataset instead of the 500 epoch. And the custom dataset was generated from data used in the Model 2. And you can see from the diagrams, it's trained with an 80% training split and 20% validation split, and achieve around 80% of the accuracy. Right, training around 80% of this accuracy on the custom dataset. So with this ResNet 152 model, newly trained on custom dataset, the superior classification performance can be achieved as compared to model trained in the means and the AZ datasets. So you can see that now it's able to correctly classify G as G, so instead of G as C. So the experimental result of the model will be tested on unseen images, and we emphasize on this focus on the serial plates in poor condition due to rust and defacements. So here we use a 10 image unseen. I mean, we can always increase this, but due to the current limitation in the computational resources that we have. And the experiment result 1 on this table, you can see that uncrop, there's a few different type of image. One is uncrop, crop, uncrop, crop, and so on. You will find that the uncrop image achieve a better accuracy, classifying the bounding box of 79%, while the crop image perform not as good, is 70%. Classification results were the best when the uncropped image was processed with inversion, okay, achieving around 92% of bounding box classifications for uncropped image. So we compare the 5 good image and 5 good crop image on average. The uncropped image achieved a better accuracy at around 85%, while the crop image performed only 58% due to probably some of this part of this image has been cropped. So the classification result were the best when the uncropped image was processed with inversion, achieving 89% for the uncropped image. So when you look at the overall result here on the right hand side of this table, both non-processed and image applied with inversion actually can identify the results for 87% and 90%. So the poor bounding box classification mainly stem from improper ROI cropping from Model 1, result in some of these disappearing in the bounding box. That should be captured by Model 2. And for experimental, you look at this, we talk about the after we create the bounding box ROI for Model 2, the bounding boxes are classified individually using the Model 2 and the ResNet 152. And you can see that the 152 or ResNet model exhibit a lower accuracy in classifying bad image as compared to YOLOv5. Is still very bad, is better than ResNet. And conversely, the crop unprocessed one and processed image demonstrate superior classification result in overall, as you can see from here. So you can see that for YOLO model achieved 94% overall, while ResNet is not as good, 58%. For classifying good image, YOLOv5 performed better on uncropped image at 86% compared to 81% for crop image. ResNet excel in classifying crop image at 71% as compared to 60% for uncrops. So both unprocessed or pre-processed method yield favorable results, with inversion process slightly outperform in accuracy. Okay, so the inversion process, pre-process is better. Overall, the crop image excel in classifying alphanumeric characters, with YOLOv5 achieving 88% and ResNet is only 64%. So conclusively, we can say that unprocessed or processed image yield desirable result with no standout techniques. So in short, we just want to conclude the YOLOv5 surpassed the ResNet in text classifications. A crop image is better as compared to uncropped one, and the text classification in performance reached 89% and 90% for non-crops, and crop image with image inversion, which is very good as I mentioned. The optimum text classification occurred with the crop image using inversion of -0.5, achieving 90%. So these studies suggest that applying the image inversion before fitting image into a combination of Model 1 and 2 to extract ROI and classify serial plates, which is better. This approach achieved 90%. However, the Model 1 required retaining on the larger dataset for improved ROI extractions, enhancing bounding box classification chances. So despite YOLO reputation for object identification and secondary performance in alphanumeric characters, we also compare the ResNet but ResNet is chosen for its stabilities, but we only can achieve 94% on the crowd image despite training on the imperfect data set. So I believe researchers in the future can always explore more newer YOLO version, which is I think V8, V9, for potential differences in the result, and we can make some comparison with that. Thank you very much for your attention.